Welcome back to the deep dive. You know, if you rely on electricity, and let's face it, who doesn't, then you know how much batteries matter. Everything from your electric car to the grid itself.
Absolutely. And today we're really zooming in, going microscopic, to understand a major hurdle for the next generation of batteries and, well, a pretty clever solution.
Right, because there's this big problem looking inside them, isn't there? Something limiting how powerful and safe they can be.
That's it. We're talking about lithium dendrites. Tiny, tiny little metallic whiskers, almost like branches, that can grow inside the battery.
Whiskers. Okay, that sounds fuzzy, but I gather they're actually quite dangerous.
Oh, definitely not fuzzy. They're pure lithium metal.
Yeah.
And if they grow too far, they connect the positive and negative sides of the battery. That's an internal short circuit.
And that's the failure point. The thing that can lead to overheating, fires. The kind of problems we need to solve for EVs and grid storage.
Exactly. So stopping these dendrites is critical. And that brings us to the focus of this research we're diving into.
Sure.
A specific ceramic material called tantalum-doped lithium lanthanum zirconium oxide. Bit of a mouthful.
Okay, let's call it LLZTO then.
The LLZTO, yeah. It's a leading candidate for what we call solid-state batteries.
Right, so the idea is to replace the liquid part in current lithium-ion battery.
Precisely. Conventional batteries use a liquid electrolyte. That's the medium that lets the lithium ions move back and forth. But those liquids are often flammable.
Not ideal.
Not ideal at all. So the goal with next-gen batteries, lithium metal solid-state batteries, is to use a solid electrolyte instead. Something non-flammable, like this LLZTO ceramic.
Okay, so LLZTO, what makes it special? Why this particular ceramic?
Well, it's got a couple of really good things going for it. It's known to be a very good conductor for lithium ions, which you need for performance. And it's chemically stable when it's right up against lithium metal, which is crucial for these next-gen designs.
Sounds promising. A solid, stable conductor. But you mentioned dendrites are still a problem, even with a solid.
Yeah, that's the catch. You'd think a solid block would stop them, but the dendrites are sneaky. They don't necessarily have to burrow through the main crystal structure. They find the weak spots.
The seams.
Exactly. When you make this ceramic, you typically press and heat a powder. This forms lots of tiny individual crystals or grains packed together. The interfaces between these grains are called grain boundaries.
Okay, so if I imagine the ceramic like floor tiles, really strong tiles, the grain boundaries are like the grout in between.
That's a perfect analogy. The tiles themselves are strong, but the weeds, the dendrites, tend to sprout up through the grout lines.
Okay, so the dendrites preferentially grow along these grain boundaries.
That's what the evidence shows. So the researchers thought, okay, if the material itself, the LLZTO, is fixed, maybe how we put it together matters. Does the manufacturing process affect the strength of that grout?
Right, this is where it gets really interesting because the study didn't just test LLZTO, they compared 2 different batches of it.
Exactly. 2 batches made using different methods. And the crucial part is chemically, they are basically identical. Same composition, same density, same overall ability to conduct ions.
But they behaved totally differently when it came to dendrites.
Totally differently. The difference was all in the microstructure, how the grains were arranged.
So let's break down the 2 methods. What was the sort of standard way of making it?
That's a method called solid-state reaction, or SSR. It's pretty conventional for ceramics. You mix the starting powders and bake them at very high temperatures, like 1100 degrees Celsius, for quite a long time, maybe 6 hours or so.
A long, hot bake? And what kind of structure does that give you?
It tends to result in relatively large crystal grains. In this study, the average was around 8.9 micrometers. Some were even bigger, up to 20 micrometers.
Okay, so SSR gives you, using the analogy, bigger floor tiles.
Got it. Now, the other method they tested is newer. It's called the Pyrochlore-to-Garnet method, or P2G.
P2G sounds reactive.
It is. It's a reactive sintering process. Instead of just baking powders, you use precursor materials, including lithium hydroxide, which actually melts during the process.
Oh, interesting. A liquid phase involved.
Yeah, the lithium hydroxide melts and decomposes into lithium oxide, and this liquid helps the reaction happen all in one go, forming the desired LLZTO structure much faster and densifying the material simultaneously.
Faster is good. And what does this P2G process do to the grain size?
It makes them much, much smaller. The average grain size for the P2G material was only about 2.9 micrometers.
Wow. Okay, so nearly 3 times smaller grains compared to the SSR method.
Exactly. And they used a whole battery of tests, things like X-ray diffraction, XRD, X-ray photoelectron spectroscopy, XPS, reflection electron energy loss spectroscopy, REE, LS, just to double check that. Yep, chemically and electronically, these two materials were the same. The only real difference was the grain size, the physical architecture.
Okay, now here's the part that feels backwards to me. If the dendrites grow along the grain boundaries, the grout lines, and the P2G method gives you much smaller grains, doesn't that mean you have more grain boundaries, more potential paths for failure? It feels like you'd want fewer, bigger grains, fewer cracks. Why would smaller be better?
That is the counterintuitive finding, and it's why this study is so important.
Yeah.
You're absolutely right. Conventional thinking might suggest more boundaries equals more failure points.
Right.
But the results were the complete opposite. The small grain P2G material was significantly more resistant to dendrite growth. It performed much better.
Significantly better. Like, how much better are we talking? What did the electrical tests show?
Well, they measure something called the critical current density, or CCD. That's basically how much current you can push through the electrolyte before it fails, before it short circuits.
Okay. Higher CD is better.
Much better. So, using a technique called linear sweep voltammetry, or LSV, the small grain P2G sample could handle over 1 milliampere per square centimeter.
Okay. And the large grained one?
The large-grained SSR material, tested under slightly different conditions, called galvanostatic cycling, consistently shorted out at much lower currents, around 0.1 milliamperes per square centimeter.
Wait, 0.1 versus over 1. That's like a 10-fold difference just from changing how you make it.
At least, it's a dramatic improvement in resilience.
That's incredible. Did they look inside afterwards to see what happened?
They did. They did postmortem analysis using scanning electron microscopy, SEM, and the pictures tell a clear story.
What did they show?
In the large-grained SR samples that failed, you could see lithium metal deposited deep inside the material, clearly following those large grain boundaries. The dendrites had basically run wild through the bulk.
Okay, so the weeds got right through the big cracks.
Exactly. But in the small-grained P2G samples, even after testing, the lithium deposition was mostly confined to the edges, right near where the electrode touched the ceramic. There was much less evidence of lithium penetrating deep into the interior along the grain boundaries.
Wow, so the structure itself seemed to stop them much more effectively. Okay, so why? What's the mechanism? Why do more smaller pathways actually resist the dendrites better?
The main idea they propose is about homogenizing the current flow. Think about it like traffic again.
Okay, a traffic analogy time.
Right. If you have large grains, that's like having only a few big highways. If there's one tiny flaw, one pothole on one of those highways, maybe a slightly weaker spot on a large grain boundary, all the current, all the traffic gets funneled towards that weak spot.
Creates a bottleneck, puts all the stress right there.
Precisely. That concentration of electrical stress makes it much easier for dendrite to start growing at that point.
But with the small grains.
With the P2G material, you have lots and lots of smaller roads, smaller grains. So the current, the lithium ions, have many more parallel paths to take.
Like having more lanes on the highway?
Exactly. It distributes the traffic much more evenly. It homogenizes the flux, as they call it.
Yeah.
So you don't get that intense concentration of stress at any single point. It spreads the load, preventing that localized failure.
That makes a lot of sense. It's not about the number of boundaries, but about how they distribute the flow, prevent the gridlock.
That seems to be the primary reason. But there might be a secondary factor, too.
Oh.
Remember, the P2G method involves that melted lithium hydroxide, that liquid phase during sintering.
Yeah, the reactive part.
Well, it's possible that how the grain boundaries form during that rapid liquid-assisted process is different. Maybe the P2G method inherently creates grain boundaries that are just tougher or less prone to lithium penetration compared to the boundaries formed during the slow solid-state bake of the SSR method.
So not just smaller tiles, but potentially stronger grout, too.
Could be. It's harder to prove directly, but it's a plausible contributing factor. The way they form might make them intrinsically more robust.
And this all ties back to manufacturing, too, right? You said the P2G method was faster.
Much faster. It forms the desired garnet structure and densifies the ceramic pellet in less time compared to the long, high-temperature SSR process.
So that suggests it might actually be easier, maybe even cheaper, to scale up for mass production.
That's the hope. If you get better performance and potentially faster manufacturing, that's a huge win-win for solid-state batteries. It really shifts the perspective.
Yeah, it shows that just tweaking the internal architecture, the microstructure, can be as important as finding a whole new material.
Absolutely. It's about controlling things at that tiny scale.
Okay, so let's recap this for everyone listening. The core finding here is really elegant. By changing the way you make this ceramic, tantalum-doped lithium lanthanum zirconium oxide using this P2G method,
Pyrochlore-to-Garnet.
right, P2G, you create much smaller, more uniform grains. And counterintuitively, this structure with more grain boundaries is way better at stopping those dangerous lithium dendrites.
Yeah, it tackles one of the biggest safety and performance bottlenecks for solid-state batteries head-on.
And the payoff, if this can be scaled up,
Potentially huge. Think electric cars that can charge much faster because the electrolyte can handle higher currents safely. Think grid storage batteries that are more reliable, last longer, and don't have the same fire risk as current tech. It addresses fundamental limitations.
it's just amazing to think that getting to that future, faster charging, safer energy storage comes down to controlling how atoms are arranged on the micrometer scale, making sure the tiles and grout are just right.
It really is. This deep dive shows that sometimes the biggest leaps forward aren't about discovering exotic new elements, but about mastering the architecture of the materials we already have. How you build it is everything.